Okay, Bismillah ar-Rahman ar-Rahim. Peace and blessings upon you all. Assalamu alaikum wa rahmatullah. Dear students, what we have done so far is we did the process scheduling, okay? And in the process scheduling, where are we? We did first the first come first serve, the simplest one. What happened in the first come first serve is you do the processes in the arrival time. The process which has come first will be served first. Simple as it is. It has a very simple approach, nothing to do, no more complex logic, but it has a convoy effect. We know, say for example, we've got a process 0, process 1, process 2. So it has a 20, and this was having a 1, and this was having a 3. Say processing time. Now you will say the arrival time of this was 0, or it may be arrival time may be same. Say they have come all at the 0 time. They have come all in the beginning. First come first serve will go first to the 20, then 1, then 3, and this was having a more waiting time, average waiting time for these guys, because they have to wait for the big process to finish. Okay, then we say okay, we will do because this was again a non-preemptive. Okay, non-preemptive, we got two first, FCFS and SJF, shortest job first. Okay, then we see that, hey, why not do the shortest job first? That we do first this guy, then this guy, and then the 20. So 20 have to wait for just a 3 unit of time, but this one has to wait for 20 units of time. This 3 has to wait for 21 units of time. So this 20 has to wait for only 3 units of time. So waiting will be only 3 for this 20, and these guys will have manual waiting time. So it will dramatically decrease the waiting time, average waiting time. So every process will be happy in case of SJF, but there were some problems with the SJF. Number one was that if we have a scenario like this, that it seems okay, the convoy effect is in FCFS, but in SJFS also there will be, for example, at a P0 0 times was 20, but at that moment, say for example, at 1 time this P1 came. Now when you want to execute, you have no choice but to execute the process has come out of the 0 time, that is 20, which has a 20 burst, that's P0, having the burst length of 20. Okay, so that means you have no choice but to execute the P0, because P1 is not arrived yet. It is arrived after the 1 unit of time. At the 0 unit of time when it started, actually it was not there, so you have to actually process P0. Okay, now this is SJF is a non-preemptive. That means once it is given the processor, you can't snatch it, you can't preempt it. Okay, you can't relinquish the CPU. That means you have to execute 20 to its fullest. So in this case, again, a P1 has to wait for this process, even at the 1. So in the beginning, P0, you give it, you have to give it up to the 20. Even at the time 1, the P1 has come, but you can't give it. Why? Because this is non-preemptive, SJF. So you have to give it a full. Then you will load the P1, and then you will load the P2. So this will be same as the case of the FCFS. There will be no difference between SJF and FCFS in this scenario. So SJF will be only beneficial if every process has come, all processes have come at the same time, and then we can see which one is the shortest, and we can actually assign them in that shortest job order. This was the one solution. This was one problem. Okay, so you can actually mitigate that problem. We said, hey, why not make it preemptive? This was non-preemptive. Okay, why not make it preemptive? That is SRTN. We did SRTN in the last video. We say, hey, you're gonna P0, you start giving the P0, but at 1 we saw the P1 has come. Okay, when the P1 has come here, this guy will have a 19 remaining time. So this has only 1, so we will start giving P1. Okay, after P1 will finish, so for example here is the 1 unit only. At the unit 2, the P1 finishes. At that time we have say at the 2 time P2 has also came at time 2. Now at unit time 2 we have 2 processes in contention. One is the P0, one is the P2. The P2 has the least time, and the P0 has the more. It does not have a shortest remaining time next. So shortest remaining time is this guy. So I will load the P2. and after that I will go these 19 of P0 again. So I preempt P0 here and reload it here. So this is the shortest remaining time. It will decrease the the average waiting time dramatically. So this was a solution to the SJF, this convoy effect stuff. Okay, but the problem which still remains there is, for example, here I will say it. The problem still remains there because, say for example, you start executing P0 in this scenario. I'm saying only, and then the P1 came. Okay, so you are giving P1 because it was shorter than the P0. P0 is 19, so you start giving P1, and the P2 came in the meantime, and P2 again is a shorter than the P0, so you give P2. Now maybe P3 comes, which is again shorter than the P0, so you can't allocate P0, so you have to wait. P0 has to wait. Now maybe P4 come and so on. The shortest jobs are started coming. If P0, P4, the shortest jobs have started coming, this P0 will simply starve. Okay, so that's why it's a starvation problem, because this will get never a processor unless if the short jobs start coming. So it's gonna actually stay there forever. Okay, so what do you do for that? The fix for that is, today's lecture. These things we have read actually in the previous lecture. So what we do is what's called the priority scheduling. So what is priority scheduling is, we give some priority number, integer, with every process. Okay. Now CPU is allocated the process with the highest priority. Okay. Smallest integer is the highest priority. We can say that. If someone has a priority of 0, it will be given first, priority of 1, priority of 2, and so on. Okay. Now we know the process with the shortest job in this case will be given the priority. Okay. So that is why I'm saying that P0 will be given the priority because it was the only process there. Then P1 and P2 and P3, if all these processes came, they will have a higher priority now than the P0. But what will happen is, if the short jobs start coming, okay, P0's priority starts getting increased. What we do is we start increasing the priority of somebody who is waiting so long. Okay. So what's literally called as aging, we call it as an aging, that if your process is starting, because what will happen if P1, P2, P3 are all lesser than 19, because I say its remaining time is 19, okay, so technically you can't allocate P0 again if the processes which are coming are lesser than 19. In a SRTN, you can't give them. So what I do is, in this case, this P0 will get starved. So to reallocate it again, what we do is we start an aging concept in SRTN, that we do this is what's called priority scheduling, that we start increasing its priority. Okay, till what will happen is we have priorities with these processes as per the shortest jobs we know, but now this guy is, even though it was a long job, but its priority starts getting increasing, and one time will come that its priority will be higher than the any job which is coming. Okay, so that means we have to now allocate the P0. Okay, so that means what we have to do is we have, basically it will have a higher number, that means low priority. So when it starts aging, we will decrease that priority until it hits maybe 0. That means it's at the high priority. Now you have to allocate P0 rather than any shorter job. Do you understand? Does it make sense? This is what was here. Okay, the starvation problem. Because low priority process may never execute, so you concept of the aging comes up. So you progressively increase the priority of the process until it hits 0. So that means you have to now allocate it. Okay. Even though there will be a tie between the priority between the two processes, the aged process will be given a chance. Okay, that's also but there is a bigger problem. We solved one problem in SJF, that was it was non-preemptive. We tried to preempt it in SRTN. Then there was a problem of starvation. We did the aging. But the big problem with the SJF and all this SRTN stuff is that you are saying that this process is longer, this process is smaller. So you're actually predicting the burst length of a particular process, which is not practical. It's simply not practical. Why? Because processes are coming. How you know that how long it is? It's very tough to say. Yeah, in many cases you can say, for example, you have a print read, you have a disk read, you have a lot of things which you know that this will take this much of time, but still you can't be precise. Okay? You can't be precise. You can only estimate and you do guesswork. So you're doing all the guesswork, so you can never exactly say what is the burst length of particular thing. Okay, you can never say that this job has this much of burst length. So you are saying the short job first is actually a bogus. Why? Because which job is short, which job is long, you can never say it exactly. You can do some estimations. Yeah, if the processes are running, you are having a log of those processes. Now after that, if they come again, you know this process runs this much of time. Okay, but in the beginning, how can you say some process is short and some process is not a short? So it's not a good idea, and it's again it's not practical. So what we do is we have a next preemptive algorithm, what's called a round robin. So round robin is basically same FCFS, okay? But what you do in a FCFS queue, you do time slicing, okay? So what is called time sharing preemptive scheduler. We are giving, some, not necessarily one time, some time slice we give, say in milliseconds. Say one time means here the 20 milliseconds. This is what is the one time means. Some unit of time you are giving. Okay, you give some chunk of time, say 20 milliseconds, 4 milliseconds, 10 milliseconds or so, and okay. And if a process has, say, for example, you are giving 4 milliseconds. If a process is just the burst length of the process is just a 2 millisecond, so it will take only 2 milliseconds and it will relinquish CPU of its own. That's what's called a block itself. Or if it has a more, say you got 4 chunk quantum size, we call it many times we call it a time quantum or quantum size. If this time slice is or quantum size is 4 and you have a 10 burst length, so you will be given a 4, then the CPU will be taken from you. Okay, you will be put on the back of the queue. Okay, so this is what is here we say. So if it uses entire time slice, then preempted and put at the end of the ready queue. Okay, because it's not having any interrupt or IO, it is ready, but your time slice is only over. So you are done what? We have a queue of processes. Say for example, P0 is here, P1 is here, P2 is here. Now you are executing P0. Its time slice is over. What you do is you keep it on a back. Now you start doing the P1. Okay, you start servicing the P1. You give 4 time slices to P1. If it is finished, okay. If it is not, the rest of the it will be again put to the back of the queue, and that means after some time the P0 will get automatically some time. So you don't need any priorities here. You don't need any, you don't need to know what how big or how small any job is. So you're not saying, hey, I'm doing a short job first or whatever this. I do it on the arrival time. Okay. That's why the ready queues manager in the first order, simplest one. And it's treated as a circular queue. Okay, circular queue. So if there are some n processes on ready queue and the time quantum is q, so we know 1 by n time of the CPU in chunk of Atmos queue time units will be given to every process. Okay, so no process wait for more than n-1 times q time units, isn't it? Okay, the important thing here is how big this quantum size should be, or this time slice should be. If Q is very large, it will become a round robin. This round robin will become actually FCFS. And if it is very small, then you will defeat the whole thing of the scheduling, because the CPU will be doing only context switch. This is what I'm saying is, say for example, we've got a P0, P1, and P2. Now P0 of size 10 and P1 is of size say 5 and P2 is of size say 4. Now you are giving 4 quantum size of 4 you have. Okay. Now what will happen? You will give first P0. You will start giving P0 its 4 quantum units. Okay. So it is 10. So 6 is left. Okay, but what we'll do is this will be kept in a back of the queue. So first you have to say P0, then P1, P2, first in first order. If this is first, do it first. If this is second, do it second. If this came third, do it on the third time. Now you are giving 4. Now you will start executing P1. Okay, in a first come first serve basis, but in a time shared manner. You will give it a 4 quantum time, so up to 8. So 4 is done. 1 is left. Okay, now 1 is left of P1, and you start giving the P2, and it is exactly having 4, so it will be done in a 4 units of chunk. So we have a 12 at 12 P2 will be done. Now after that P0 will be loaded again to give it more 4 units. Okay, that is 16 here. So you are giving 4 units, 2 is left. And P1 is only 1, it has 1 left, so you will give the P1, and after that you will start loading your again the P0 of having the 2 units. So 17 plus 19. Okay, so in this manner you are doing it. But the thing is that if you have, say for example, time quantum of 4, say you will say big time quantum, say you are saying the quantum of say 10, okay, or 20 or something like that. So what will happen with this? The first P0 will come because quantum is 10, it will take up the whole 10 unit of time, so 0 up to 10. Then will come the P1. P1 will take the 5 units of time out of 10, so it will relinquish because it is still 5 units, but it does not have that much of burst length, so it will leave the CPU. Then you will load the P2. So it will be nothing but a first come first serve, right? So it will be nothing but a first come first serve. There will be no gain, so you're not going to do this. So time slice should not be bigger. Okay, if it is smaller time slice, say 1 unit, so you say P0, then you say P1, then you say P2, then you say P0. What is happening when you are actually preempting P0? You have to save everything of P0 in a PCB, which we discussed in the previous videos. Okay, and then you have to load all the context of the P1 from its PCB. So it is kind of, you are doing context switch, too much of context switch you are doing. So you're wasting a lot of time. We know CPU is wasted, CPU time is wasted in the context switching. So you're doing a lot of context switching, so you are doing no job but only preempting and non-preempting. You are only saving the PCB of one process and loading the PCB of another process. The main maximum CPU time is going into that. So it will defeat the whole process of scheduling. So that means we need to have an optimal, time slice in this. Okay, let's take an example. Okay, let's take this as an example. You see P1 has a 24 processing time, P2 3, and P3 3. Okay, and we're using 4 milliseconds as our quantum, time quantum or time slice, whatever you call it. So P1 will get a 4 units of time. Then P2 will be loaded. It gets a 4 units, but it's only 3, so it will take a 3 units of time. That is 4 plus 3 is 7. And then P3 will load. After that, it's again 3 units of time. So it will not be having the full 4 units. It will have only 3 units of time. 7 plus 3 is 10. And then you load the P1. You have only P1 here. This is a very simple example. Then you will say 4 units of P1, 4 units of P1, 4 units of P1, and so on until it does not finish it. Okay. So it will be finished here in this time. Let me go it like this. Okay, in 30 units of time, it is finished. So what is going to be turnaround time for P1, because it's finished in 30 and it came at 0. So 30 is the turnaround time. Say we are assuming that everybody came at 0. Okay, this is 3 minus 0. It is completed as a 7. 7 minus 0 is 7. And for P3, 10. It is finished at 10. 10 minus 0 is 10. And what is the waiting time? Turnaround time minus processing time. 30 minus 24 is 6. 7 minus 3 4, and 10 minus 3 7. And you do the average turnaround time, average waiting time, and you see 15.66 and 5.66. And then throughput is 3 over 30 because you completed it in 30, the 3 processes, so 3 over 30.1. Okay, and process utilization 100% because we have nothing idle in between. Anyways, so this way you are actually removing all the deficiencies of SJF basically. Okay, like we say that we need to know how jobs are big and how jobs are small. You don't need to do it here, right? because you are running the processes, the time slice. If it's finished, it's okay. If not, it's coming on a back queue. It will come again, and so on. Okay, okay. But there will still be some problems. What kind of problems we have? Okay. For example, you are saying P1 and P2 and P3 is the processes with the burst time of this much, but we know processes have the burst time, processing time, as well as some idle time where it has to do some I/O. Now maybe if we are mixing the I/O based processes and processing which needs more processing, so processor based processes and the I/O based processes together in this fashion, it is gonna waste time. It is gonna go for more context switching and all. So what are you gonna do? We got to do something else, that we want to make separate queues for the different kind of processes. That's what's called the multi-level queues. Okay. Let's take a more example of round robin in this video and take a multi-level feedback queue in the next video. I usually take these examples from the internet. They have made it already, so I don't want to make it waste time in making of these of my own. I will only explain things. These are already ready-made PPTs and all. From a lot of books, we have PPTs. Okay, your Dragon book and all. They have the PPTs online, so no need to make them of your own. So this is the processes with the burst time, and say we have here the quantum of 20. Okay, so you are given 20 slices to everybody. First P1 20, then P2, then P3, then P4. Then P1 comes back because if you give 20, it will have some how many? That is 33 will be left. So you have to give P1 again here. Okay, then you will load P1 again here. So you give P3 because P2 will be finished. So P3 will, after giving 20, will have 48 left, and this will have a 4 left in the first round. So P1, P2, P3, P4, and out of it P2 is done. Okay, here, and now you give again P1 20 slice, so 13 will be left in it. Okay, then you give P3 20 slice, 28 will be left. Okay, and here is a 13 left. Let me wait a second. So you are 13 left, I guess. Okay, 28, and now after that P4, you give P4 4 time slices, and it's done here. So P4 is done here. Now you give 13 units of P1 here, so P1 will be done here. Then P3 will be given 20 time slice here, and then 8 time slices here. So P3 is finished here, right? P3 is not finished here, P3 is finished here. So accordingly, you will calculate the turnaround times and the average waiting time. And one thing you must note, that in the round robin, okay, we'll have a higher turnaround time. So TG time will be greater than SJF, shortest job first. But what will happen is it will have a much better response time. Okay, that will be much higher. So now that's enough for this, and now for next we will have, because of the different nature of the processes, some processes like to be in a batch mode, some are interactive, okay, some are less interactive, some are I/O based, some are CPU bound, and some are actually I/O bound, and there are so many other kind of processes which try to stay best fit for some type of scheduling algorithm. So better is we make some policy which is having multi-level feedback queues. So this will be now our next chapter. So with this, we came to the end of this segment. Okay, so always stay smiling and take care.